Yeah, couple of logistic things. The registration deadline is done, right?
No, sir, it
It is.
extended till
They
20th.
extended.
Oh
So
my
you,
God.
you may hit a century, sir.
I don't want that to happen. Okay, so we still have class is not yet stabilized that way. Okay. Okay. Okay, anyway, let's get started. So here is the plan for today. I'll start from some basics of probability theory. One request is all of you please mute unless you have a question or something. Even when you have a question, uh, since it's a very large class, let's maintain some sort of a decorum. Please raise your hands, of course, virtually. I'll call out your name and then we will discuss. So please ask me questions. Otherwise, it will become a very, very boring monologue. First of all, virtual classes are boring because I don't get to see students' faces. On top of it, if you don't talk, it'll be double boring. So what I'll do is after like every 15 minutes or so, right, when I finish one particular concept, I'll stop and ask for questions. Please, if you have any questions, you can ask me. Even in the middle, you can, feel free to just raise your hand so that I can stop and address your questions. So, okay, I hope that you have gotten access to my course notes and that feedback form that's out there and all that, right? So all the logistic issues are sorted out, I suppose. No, no further questions there, I think. Teams. Oops. Will not acclimatize with this OneNote thing, so struggling just a second now. So where do I go to that class notebook? Okay, got it. Welcome to OneNotes. Okay, but
So you're not sharing the screen.
read only. To edit, tap the OneNote icon. Where is the OneNote icon here? This one? No, this one. Okay, yeah, if I share, you can help me perhaps.
It will be on the top right, sir.
Let me just see. Been
The
using
small
this good
icon on the top
notes.
right.
Share screen. Share start broadcast.
It's visible now, sir.
Uh-huh. Uh, where is it? To edit, tap OneNote icon.
On the
Where is
top
that
right.
icon? Oh,
On the
this
top
one.
right, just yeah.
I see, I see, I see. Got it. Okay, great. Thank you. Hmm. So, okay. So, shall we have like one different page for every day? I think let's do it that way.
Yes, sir, that will be better.
The date will always be here, I suppose, right? I mean, it will be Saturday, August 10th it is. So, we'll have to delete this. How do I delete this? Delete. Okay. This way, maybe we will rename this as uh, not really.
Sir,
How
you can
do
Sir,
add the
within the
heading
file itself, just mention the name of this page.
on the
where?
top. If you can
Here
On
itself,
mention,
huh?
top,
The title.
yeah,
Saturday 10, just above that, mention this page title.
So, we'll do OCR, huh?
No. Yeah, I think it does.
yeah.
Replace my
So
hand.
both
It
will
is
work. Both will work. Keyboard and OCR both.
Ah, yeah. Yeah, I need 2-3 minutes for this pencil to get charged. Anyway, so I'll write that. So today's agenda is the following. I'll start with the basics of probability theory, the probability theory that we would need to continue in this course in the first half. The second half, introduce you to the generative models and formulate it if possible. So that is the agenda. Okay. So now the fundamental question that is to be asked is, right, you know that most of the machine learning, right, or all of machine learning is based on this branch of mathematics called probability theory, right? Now the question is, why do we need? It's actually a new paradigm. I mean, new meaning it's a see when we start when we start studying mathematics, right? We have numbers, we have counting, and we gradually learn calculus. So if you think about it historically, what was the need for calculus is uh, calculus had to be developed because this idea of rate of change of things and the idea of calculating the area under an arbitrary curve, right? That had to be that was important. For instance, people like Newton, they wanted to find out what was the total distance covered by a moving body whose speed or velocity is plotted as a function of time. Now, there was no tool that time, okay, that could deal with such kind of questions. So he invented a new set of tools, right, which became a branch of mathematics called calculus, which was developed uh, subsequently. So similarly, probability theory, right? Statisticians had this question from a long time. The fundamental question is, all machine learning is studied, right, or rather modeled from a probability theory perspective. Question is, see, it is not a force fit in the sense that people don't, or rather, people didn't come up with probability theory, or rather, apply probability theory because it was there. It was not that. The idea is that you cannot answer a few questions that you often encounter in machine learning or rather statistics if you do not have this tool called probability theory. So that is the prologue. There's absolutely no way you can answer a few questions. See, just like you can't answer questions like, suppose I draw an arbitrary curve, right? Or rather, I plot some measurement that I make, speed measurement or something as a function of time. If I have to find out what is the total distance that was covered by this particle or a moving body, only when I have speed as a function of time, you can't answer that question if you don't have calculus, isn't it? Because you need the idea of like integration, which is area under the curve. Otherwise, you can't answer that question. Similarly, there are questions that you can't answer if there is no uh, if the tools of probability theory are not in place. So a lot of people tend to think, right? Oh, maybe it was a force word. People talk of probabilistic machine learning because it's just there, etc. It's not that. It's a tool that is absolutely needed. There is no other way to handle or rather answer a few questions that arise without having this versatile tool of mathematics called probability theory. Okay. So that's, I mean, what I'll do today is that I'll try to convince you that what are the kind of questions that cannot be answered by any other branch of mathematics, right? You need to develop a special branch of mathematics called probability theory and just develop some background there so that, yeah, sufficiently charged, develop some background there so that we can, I mean, all of you already know this, I'm sure, but still just to get your memory and get up to the speed, we'll do that. This we will put as doesn't seem to do a good OCR, right?
Keyboard will be better, sir. Yeah. Keyboard script will be better. It will be more visible.
You're saying I'll have to toggle the keyboard. Okay. Great. This we will see intro. Introduction to
So at the beginning, can you put lecture number as well?
um, okay. Okay, so let's get started. Okay, so what is the as I said, what are the kind of questions that we are interested in in this statistical branch of statistics or machine learning is? We'll say so fundamentally. For most problems in science and engineering, let's just go. Is there a see when I place my hand on top of my iPad, no, it's just going everywhere. Is there a way to control that? Use this.
So you can enable the second last option right next to drawing mode.
This one?
Yes.
What is this?
So that will allow only the pencil to write.
It's palm reject.
This palm reject. Oh, great. Thank you. It should be there, but I don't know where it is. Okay. Fundamentally, most problems in science and engineering, CIE and CE are function approximations. Okay, so what do I mean by this? Uh, most problems that you get in science and engineering are concerned about function approximations. So what are functions? So now a function basically a mapping, right? That is learned between function f is a mapping that is learned between two sets called A to B, right? Where A and B are sets. Okay, so it's a rule, it's a mapping, right? That would map one set to another set. Okay, and generally, um, this set is called the domain, and this set is called the range. Okay. So there is a function, it takes an element from the set called domain and maps it to another set called range. Okay. So now we'll take examples of functions. You take some examples of functions. So let's say that there is a function, okay, that takes element from real numbers, okay, and maps it to another real number. So this is a function which maps real numbers to real numbers. Okay. This R represent set of real numbers. Set of real numbers. Okay. So this function maps set of real numbers to set of real numbers. Okay. And you can take another example where f of x. In fact, to be precise here, it actually maps of real numbers to set of positive real numbers. Correct? So R plus, so this is set of reals. And R plus is set of positive real numbers, right? So this is a function. So you can think of any, I mean, lots of such examples, right? So another example can be that you can take modulus x. Okay. Similarly, right? So this is another function that maps R to R plus similarly. So these sets, right? They need not be R. So they can be anything. So it can. Let's take another example where f of x is equal to x transpose x. Okay. Now where x, the domain, right, is in some d-dimensional real space. So what do I mean by this? This is d-length real vector. So what does this mean? This means that you all are familiar about the Cartesian coordinates, right? So you know that every point in Cartesian coordinate, if I call this x1, x2, every point in Cartesian coordinate can be represented by a set of two real numbers, right? If you take a point here, this point will be some x1 comma x2, this is another point x1 comma x2, x1 cap comma x2 cap, etc. and so on. So this is typically represented as R2, right? So these are actually called, this is a two-dimensional Euclidean space. It's named after the mathematician Euclid. Okay, it is called two-dimensional Euclidean space or vector space. Now, similarly, imagine a d-dimensional Euclidean space. So basically, this is still happening. When I place my hand, it is simply taking me everywhere.
Sir, if you are not comfortable, we can switch to good notes also.
It's okay. I'll understand this. How do I get this off? I mean, this thing. No, I don't want this. So this side pane will always be there, is that? I want this to disappear.
No,
It
you
will
can
disappear.
remove it near the settings icon, the full screen button, that should do.
Where is it?
Or you
Right
can
next to the settings button.
Setting, okay.
Top right.
Next to it, not
the
in
full
settings,
screen.
next to settings.
Top right
This one.
corner.
Ah, this full screen. Okay, great. Please keep educating me, okay, with all this. I've never used this like OneNote. That's why the issue. I'll get used to it, no problem. Yeah, I was saying, see, this thing is a d-dimensional real vector, right? So this is called, in general, this is called the D-dimensional real space. So basically, every point in this space is represented by a D-dimensional tuple, where D is a positive real number, okay? Z plus. So now, whenever I write this notation, right, I mean a D-dimensional real space. So it is the extension of the two-dimensional Cartesian space that you know of, right? A D-dimensional real space is simply points in a D-dimensional real space are simply simply the vectors, right, that are there in D dimension. Every point in that D-dimensional space can be now represented using a tuple of D real numbers. That's what I mean. Now this function that I'm talking about, which is f of x, will give you x transpose x, where transpose is, you understand what transpose means, right? Transpose operation of a vector. Now this is a function that maps Rd to, again, R plus. Now inner product can be negative as well. So it maps Rd to R. Okay, so this function takes as input a D-dimensional real vector and gives out a real number. So that is a function that would take a D-dimensional vector to a real number and so on. So, I mean, you can think of these things, right? There are multiple examples of what functions constitute. And as I said, most problems in science and engineering are the following, that given pairs of may not say it that way. Maybe I'll define it in a formal way. Okay. Suppose capital A and capital B denote the domain and the range set. Okay, domain and the range set. Now, suppose you're also given P pairs of elements xi, yi, such that now xi. So let's say that these are in such points. Xi is an element from A and yi is an element from P. Okay. So this we have to say, suppose A and B denote the domain and range sets of a function f. Okay, that takes an element from A and maps it to elements in B. So given pairs of elements xi, yi, such that xi is in A and yi, B, the question or the problem is to find the underlying function f. Okay, so this has been a problem of interest for did something. This has been a problem of interest for scientists and engineers from time immemorial, right? So if you have given some n elements, these are, you can also call these as observations. Call these as observations or data or whatever, right? If you're given this, try to find the underlying function f. So now, why is this important? Suppose you find the underlying function. What is the use of finding out that underlying function? Is that, okay, let me give you examples perhaps. So example is, now let's say A is set of positions of a planet in sky. Okay. By positions, I mean the coordinates. Maybe no, this might confuse you a little. Let's not take that example. Let me take that example next. The first example that I can take is yeah. So it's an acceleration of a body. Okay. So B can be force exerted on it. Okay. So suppose I give you I measure acceleration of a particular moving body, and I also give you what was the force that was exerted on it. So the task is to find out how are these two sets related, right? The set of force exerted on it and the acceleration that the body undergoes, right? I mean, how are they related? Okay, so this was actually the question uh, that was asked by Newton, right? Do you know how are they related? These two things?
Mass into acceleration.
Mass.
Yeah, they are linearly related, right? So now if I call the acceleration of a body denoted by A, which is a scalar. So note that set A here is set of real numbers, because in fact positive real numbers, acceleration cannot be negative, and can be negative, right? Because also has the direction. Let's say force can also be negative. So yeah, so force exerted on it is another real number, and they are, denote this by f. Then the relationship between these two, as you know, is a linear relationship, just simply given by I mean the proportionality constant is the mass. So you simply have the force is related to acceleration. It is proportional to acceleration, and the proportionality constant is the mass. Now, as I said, right, I mean, this was, why do we need, this is just one example. I'll take questions in a while, okay, Aditya, so that I can think of another example. And somebody give me an example of a case where the function is not linear.
Energy
Kinetic
maintenance.
energy, kinetic
Come again?
energy to kinetic energy to velocity.
Okay, how are they related? Kinetic energy and velocity.
Half mv square. E is equal to half mv square.
Yeah. Velocity is v and energy is E. Okay, we can do that. Set A is velocity, B is energy. Right. So there the relationship is and so on, right? I mean, now you get the point. Now, here, right, I mean, lot of scientists and engineers, they wanted to figure out this relationship, right? I mean, a lot of research that people were doing was focused on finding out the relationship between the measurements that I have done. And these measurements are represented as the elements of sets. So mathematically speaking, as I said, right, if you look at my initial statement, I said that most problems in science and engineering are function approximations. Uh, what I mean to say is that suppose there are two A and B are two sets, which are the domain and range sets of a function. And if you are given elements which are pairs from these two sets, okay, the underlying problem is to find out or identify what the underlying function is that relates elements of A to elements of B. Now, why is this question important? So the next thing is, what do we get if we approximate the underlying function? Okay, so now function approximation. Can somebody tell me why is that important? Why do you have to relate quantities, measured quantities?
Predictions.
Exactly, right? So one of the things is function approximations. Approximation, okay, enables predictions. So what do you mean by prediction? So we have to define this, right? So prediction mathematically is simple. Prediction is that find the element in set B, which is the range set. Okay, corresponding to any element in it. Element in the domain. Okay, this is important, right? So now, if you look at it, the data or the observations that we have done, okay, is there a pointer here somewhere? Like without writing, can I just point to things? Because in GoodNotes, it used to be there. Highlighter is there. I don't need highlighter, like a cursor or a pointer of sorts. Do you know? Anybody knows? See, what I want to do is I simply want to like show this, right? Just highlight on this. I keep doing this because when I write something, I go back and just show that. Is there something of that sort here? Stylus orientation. Okay. Does anybody know that? No?
So there is no pointer.
There's no pointer here.
No, you can maybe use the assistive touch button on the right side to kind of circle around things, but that's about it.
I see. But it'll just stay away, no? I mean, I don't want that to stay. I just want to point out to that thing. Yeah,
I
somebody
think you can
should.
use
Huh.
pen as pointer if you click on the pen itself.
Meaning? I didn't get that.
I mean, if you click on the pen, I guess you're supposed to get some menu.
This one. This one,
Yeah.
something.
No, I mean on the pen itself, like the whatever you have it highlighted. If you happen to click it again.
Okay. Now,
do you see any options on or
Can you click and hold that pen once?
nothing happens.
No.
Anyway, so find it out. I mean, if any one of you want to find that out, let me know. Or just tell Microsoft to have that feature in the next version. It's very, very useful. For example, I'll show you in GoodNotes. There was this thing, you see? It was so nice. I'll just go away. So if there is something that I write, I can go back and just mark this and talk about this, and it was very, very useful for me. You see that red mark? Here it is not there at all. So
If you go back to the pen gallery, I think there is an option.
is there? Okay, let's see.
So there is a plus button next to the pens, right?
Correct. Highlighter.
So select the pen mode and
So,
it says
yeah.
that use pen as a pointer. I don't know where to get this.
That's only on Windows.
Oh, okay.
Okay. Fine. Okay, fine, whatever. So I'll have to maybe just go back. It's not very optimal because I keep using this pointer so many times while I was teaching. It was very useful for me. Anyway, okay.
You can use the other app and later upload the notes here if you'd like.
Well, that's also fine. That's what I was doing, but people suggested this one notes and I just thought that it's okay. I think. Okay, no problem. Let's move on. Yeah, so what I was saying is that you are it's still okay, right? I can just point it here and some of these things will become yellow colored. I think it's fine. But when you are looking at the notes, you should just ignore these yellow colors because they only mean that while teaching, I've pointed out to them. That's all. Okay. Anyway, so let's try to do that. I mean, they are not. I mean, they are no way they are important or whatever, right? They just simply mean that while teaching, I just pointed to those things and came back. Huh? If that is okay, I can continue with this. Just use this thing and highlight it. Okay. Anyway, so what I was saying is, why do you need function approximations is that while you have observations and data for about n points, you have made n observations, we are often interested in understanding how the system behaves beyond these n observations that we have made. Otherwise, we have anyway made those n observations. There is no need in those scenarios. But we need to know what happens beyond these n observations, right? So that is what we call as prediction. Prediction is basically find the element in range, right? Find the element in the range set. In the range set corresponding to any element in the domain. So given any element in the domain, you need to understand how the range set, what element in the range set does it get mapped to, and that is what is called as prediction. So here, what you are doing is, given a particular acceleration rate that was not observed, if I want to know what the corresponding force is, then if you find that underlying function, then you can find out what the force is. Okay. Similarly, with this velocity and energy, right? And if you are given a particular velocity, if I want to know what was the energy that was exerted on it, I can just use this function and find out what it is. Now, that is one of the most important applications of why one needs function approximations. And all, as I said, all problems in science and engineering are about predicting this. Okay. Right. Any questions so far? Show of hands. Yes, Raghavendra, go on.
So is this also called as inverse problem that we talk about?
Yeah, you can call it inverse problem that way. Yeah. See, I'm actually going to bare basics of stuff. I'm sure that all of you know this already. But yeah, so I want to call it function approximation, given these pairs of observations and data, rather observations from two particular sets. I want to understand what the underlying function is. Yes, of course, it is inverse problem. See, it's not quite the inverse problem because in typical inverse problems, what happens is you only have access to output without having access to input. Or rather, you don't have elements of range set at all. Sorry, domain set at all in inverse problems. So that's why they are called inverse problems. Here, you have access to pairs from both the domain and range. You get it? That's how they are different. Okay, Arijit?
Sir, one question I have. Why do you use this word approximation?
Who is this I? Sorry. Who is talking?
Why do you have this?
No, who is talking?
Sushil, Sushil sir.
Okay. See, we have a bit of a rule in this class that if you want to talk, please raise your hands, because otherwise, no, too many people, it becomes a little chaotic. Please raise your hands. I'll call out your name and you can ask questions. Huh? Okay, thank you. Yeah, I'll come. I'll go in the order. Arijit?
Sir, one question that till now, whatever a function relation we saw between two elements is like kind of a proportional, right? Being it linear or non-linear. So one is increasing, other is increasing, or inversely proportional also. But suppose the relationship is very complex. For example, if it is too cold, I may not go out. If it is little hot, I will go out. But if it is too hot, again I will come back to my home, right? So this kind of relation where you cannot directly make it proportional or inversely proportional. So how this prediction will work there? I mean, generative model. Maybe too early to ask this. Just asking.
Good question, very good question. And yes, you see, that is why, right, we need other mathematical tools. Linearity or proportionality doesn't work. See, for instance, suppose you just measure let's say that you measure the temperature. You just heat a body, okay? You just heat a metal and measure the temperature of that metal at different points along the material. Now, if you want to ask me this question, that if I measure temperature at one point, okay, I need to know how the temperature varies across the body. How do you model it? You measure temperatures. I want to know what the temperatures are at other points of the body as well, given some heat. Now, you can't, there is no way that you can write it as a linear equation. You have to express that as a differential equation, isn't it?
Okay.
Right?
Okay.
So that's why you need another branch of mathematics, right? Which is differential calculus, and you need to express it as differential equation. But the kind of question that you are asking is the same. Now that if I have measured the temperature of a body at certain points, now if I give you the properties of that body, right, and the initial conditions, if I have to know the temperature the body is at different locations of the body, then you need to model it as a differential equation. So what I'm trying to say is, of course, the point that you brought up is very relevant. That's what I'll move on to next. There are questions that cannot be answered with these kinds of things, right? Or these kinds of existing mathematical tools, and that's why you need new branches of mathematics, and probability theory is one such. So I will give you examples, example scenarios and questions that cannot be answered using the existing mathematical tools, and that's how I motivate why probability theory is needed. It's absolute necessity. Yeah. Okay. Parth?
So my question is more about the terminology. So we are using the word prediction here, and from what we study in probability predictions, it's about an estimation of numbers, right? But in this case, functions, we are mostly talking about absolute values, and we're getting absolute answers. So why is the word prediction and approximation being used here?
Okay. See, that's a definition, right? I mean, people use different terminology for different things, right? I am using this word prediction. That's why I define. Whenever I use a term, I define what it is. To me, prediction here is simply finding an element in the range corresponding to any element in the domain. In fact, even in statistics and probability theory, when we talk of prediction, we actually are evaluating a particular function at a point. I will talk about it in a while. Okay. So you're not, there's no, there's no quote unquote uncertainty. Right? We'll discuss all that in a while, right? I mean, probability theory is a very, what should I say? It's a lot of misnomers and a lot of misunderstandings, right? I mean, people use terms right, left, and center. Even there in probability theory, prediction refers to evaluating a function, a particular function at a point. We'll talk about it in a while. Okay. Anything else? Any other question? I don't see any hands raised, so we'll perhaps move on. Now, as like Arijit was asking, right? So the problem here is the following, or rather, yeah. Now, what if the mapping between the range between the sets cannot be found out? So using existing mathematical tools. See, as he was pointing out, right? Okay, in fact, as I said, you can take another example perhaps, right here. In fact, you can write this as the problematic. Breaks the flow and makes the class up. Okay, what happened to this? How do I? This can be written as, that this is the derivative of double derivative of the position respect to time, because acceleration has to be measured and you had calculus, so you can represent that as the rate of change of dt squared. Yeah, you can represent that as the double derivative of the position, right, with respect to time. Now, the problem is, as he was pointing out, if the relationship between the elements of range and the domain, if you cannot find out, if you cannot find the functions, you can't rather express those relationships using existing mathematical tools. What do you do? The solution, this is just as I gave you the example, right? The calculus was discovered. So come up with new mathematical tools. So this is how, right, probability theory is motivated. That specifically for probability theory, the problem is what happens is, give you formal definitions of all this. So motivation for probability theory is the following: that what happens is the relations between sets to be approximated, or rather relations to be found out, are complex. What do I mean by complex? Is that do not adhere within the existing mathematical framework. Okay. Mathematical framework. Now, if this happens, then you need to come up with new way of modeling things, or a new way of expressing things. That's why probability theory becomes handy. Let me give you an example. I'll also tell you what is the fundamental idea behind probability theory. So, example is, now suppose I'm given take any ML problem, right? So elements. Let me not make it pedantic. I'm given images, okay, pictures. Let me call it as pictures. As I'm not going deeply into maths yet. So let's say that I'm given pictures. So I have to learn relationship between set of pictures, right? And the idea of gender, okay? So this set typically, right, how do you represent a picture in a computer, is that you write that as R P cross Q. Basically, it's a grid of numbers, right? What is a picture? What is an image? Basically, it's a grid of numbers. You have P rows and Q columns. Everything is a real number here, right? So you have P cross Q real numbers. That's how you represent a picture. Now, every picture is an element in a P cross Q dimensional real space. So you should imagine that just like we have the Cartesian plane, right, which is two-dimensional, there is a P cross Q dimensional space. And in the P cross Q dimensional space, every image now becomes a number. Every picture becomes a point, basically. Okay, not a number, I'm sorry. It's a point. Now, what I need is, given this, I'll have to predict, right? When you remember what the definition of our prediction is, right? I define prediction as finding out the element in the range set corresponding to any element in the domain. So now this gender is a discrete set of two values. Let's assume that it's a discrete set of two values. Now, given this picture, I need to find a function, okay, that will take an element in P cross Q dimensional space, right, which is a vector, and maps it to one of the two discrete numbers, 0 and 1. Think about it. Now, remember how these picture was taken, okay, or rather obtained. How are these P cross Q numbers obtained? Now, what is happening in the background is the following, that some person is standing, okay, standing or sitting or whatever. Now, you have a sensor, okay, which we call as camera. Now, what a light falls on that person, okay, and reflects some electromagnetic radiations back. And those radiations are sensed or captured by the sensor. And what happens in the sensor is that there is a voltage or current change that happens. And that is what is recorded as a real number here, correct? That is what a picture is. And these grids correspond to different spatial locations of the object. So what is that we are trying to do here? If you imagine, we want to relate, okay, the amount of light that a particular position reflects, okay, to an idea called gender. You see what's happening? Okay, it is very, very abstract, in the sense that, see here what happened is that in all the examples that we gave, right, force was measurable, acceleration was measurable, energy was measurable, velocity was measurable, and so on. But here, what is being measured, right, is the amount of reflectance that a particular surface is giving you. What you want to relate it to is an abstract idea, right, and a non-measurable idea called gender. Do you appreciate the difficulty in what we are trying to do? Of course, right? I mean, this can be gender, or this can be, let's say, if a person is beautiful or not. I mean, I keep making this philosophical statement that nature is very simple, right? I mean, if you want to fly an aircraft, which is a very complex task, all you need is first order differential equations and Newtonian laws. That's all. Okay, to do things like things that are as complex as flying an aircraft. But to find out, right, whether somebody is a male or a female from a picture, you need a billion parameter model. See, by the way, look at this. How many parameters that this model has? I've not defined what a model is yet, but still, this f equal to ma, how many parameters does this have? Can somebody tell me?
2.
Two.
Sorry,
One.
3.
One. It has
One
one
per.
parameter. M is the only one parameter that it has. Right? And the other example that we saw is also one single parameter model. Okay. Or if you take a second order differential equation or a third order differential equation, all it has is 3-4 parameters. So as I said, to explain nature of, you only need 2-3 parameter models. But to understand and predict things that human beings constructed, you need billions of parameters. It only shows how complicated we are as human beings. I'll give you another example for that. Let's say that you have a document. These are the typical day-to-day ML problems that we solve, right? You have a document. And what you need is the idea of emotion. Right? So what's a document? Document is collection of certain tokens, okay? So I will talk about all this, right? What is tokenization, etc., and all that. You can think of these as collection of words, keywords. Okay, all these words are represented as vectors. Okay, each of them is represented by, let's say, a d-dimensional vector. Okay, which means that this entire document now will become a point in a d cross k dimensional space. Every document is an element or a vector in a d cross k dimensional space. What you need is a function, okay, that will take an element from d cross k dimensional space, which is a document, and maps it to, let's say, that this emotion. So there are 5 emotions, right? Like sad, angry, happy, whatever, right? So represent that as 0, 1, 2, etc. So it just maps it to some discrete set of 0, 1, 2, 3, 4. Okay. So this is what we need. So what do we do? I mean, the so-called inference that we do, right, is nothing but prediction. What is prediction here? Given this particular function, if you are given any element from from the domain set, you want to map it to the element in the corresponding element in the range set. That is what is to be done. Now you know that, right? I mean, this is what things like ChatGPT, etc., do, where you can't find the relationship. What is emotion? I mean, it's like what is a positive emotion for you can be a negative emotion for me, and vice versa. So this idea of emotion is very very synthetic and man-made. Okay, so to understand how, again, if you go back to how these vectors were created, okay, if you take some like embedding like TF-IDF, which is a very primitive way of looking at expressing words, which is simply counting the number of times every word has occurred, keeping a dictionary, right? How is that related to a concept called emotion, which is a very very abstract concept? Okay, so now the problem is that because we are dealing with the relationship that are complex. Now, what do I mean by complex? Complex mean that they do not adhere to existing maths. I cannot find a linear relationship or a quadratic relationship or a differential equation or a relationship that can be modeled using a differential equation that would relate these reflectances that a surface will give to an idea called gender, or rather it can also, I mean, you can think of all the problems that you do in ML, right? I mean, take a picture and do a person re-identification where you identify what the person is, and then you can talk of any of those things which cannot be modeled using existing mathematical tools. Okay, so that's the motivation, right? Why do you need a new mathematical paradigm? Is because these functions that we are trying to approximate or find are such that they cannot be found out using existing mathematical techniques. In fact, let me tell you something. When people were doing pattern recognition using non-statistical methods, people were actually looking at coming up with these kinds of functions, right? Using existing mathematical tools, okay? That would enable them to relate uh, these kinds of vectors to these kinds of elements. Let me give you an example for that. Let me take another example. Um, sorry, so I'll take questions. Nirmit, just hold on. Another example. Let's say that you have a speech signal. Okay, what you want is set of phonemes. So what are these phonemes? I'm talking about this a, b, right, or e, and all these things. See, note that phonemes. See, what is the commonality in all this? Commonality in all this is that the range set. Let me just tell you this. The range set, okay, is non-measurable. It is not measurable, right? Or rather, I'll call this as abstract. So the idea of phoneme, right? So what is happening, just like in the document and the picture example, what is happening in the speech example is that what is that you are doing? So there is a microphone. Okay, let's say that there is a speech signal. there is a speech signal. Okay. So what is the speech signal? So I'm talking. What do I when I talk? There is a change of pressure, atmospheric pressure that is happening. Okay, because when I change, the air comes out of my mouth with a particular type of constriction from my vocal apparatus, and there is a change in pressure in the environment. And there is a sensor which is called a microphone, which is a condenser based sensor that is measuring the rate of change of pressure as a function of time. And this thing that we measure, right, and that is converting, this sensor transducer is converting the rate of change of pressure, atmospheric pressure, into voltage. And this is what you measure as speech signal. So this is time, this is the speech signal. Okay, it's a one-dimensional signal. So this is nothing but the rate of change of voltage as a function of time, and the rate of change of voltage happen because there is a change of pressure that is happening as a function of time. Okay. Now tell me that our function. So then again, you can represent that using multiple things. One way to represent that is just speech signal is a continuous signal, right? Just chunk it, just like you do it. You tokenize a document. You chunk the speech signal into parts, and you represent that as some p-dimensional vector. It's a p-dimensional vector. Now, what you need to do is, you need to learn a function that would take a p-dimensional vector, which would represent the rate of change of pressure, atmospheric pressure as a function of time, and you need to map it to an abstract idea called phoneme. Now, why is phoneme an abstract idea? So, what is a? The sound a is very abstract, right? It's only a perception-based idea. You can't measure a. What you can measure is the rate of change of pressure as a function of time. Now, you need to relate rate of change of pressure, right, as a function of time to an abstract idea called phoneme, which is not measurable. You understand? Everywhere the same thing is happening, right? So the range set is non-measurable, but the domain can be measured. Okay, so in these set of scenarios, okay, where you have measurable domain sets and abstract range sets, finding out a function that would map these two via existing mathematical tools is difficult. But as I said, historically speaking, people tried using existing mathematical machinery to solve these problems. Okay, so I'll tell you. So historically, okay, attempts were made. EMPTs attempts were made to learn such functions using classical tools, let me say it. Let me give you an example for it. Let's take the example of speech, let's say, right? So the problem is that set of speech signal to, we need to get into phoneme, right? That is what our goal is. So you know what people did? So they took the speech signal, okay? They modeled speech signal, right? As basically you model speech signal as a linear or a nonlinear system or nonlinear system. This has some input, okay? And this is the system. In LTI system, you can either make it linear or non-linear. Let's say that it's a linear system. And what you get back is the speech signal. Mischief. Okay. So this is the input to that system, and this is the speech signal that you observe. Okay. Now, what they did is, all you can measure is the speech signal, right? This particular speech signal. They say that there is an abstract input, which is the phoneme, the idea of phoneme that a person thinks of, goes as an input to this system. And this system converts that into something that is measurable, which is called a speech signal. Now, if they want to find that underlying function, okay, that would see, remember that we are interested in finding out the relationship between speech signal and the phoneme, not the other way around. Now, what they do is they model the entire procedure, right, using some system. Okay. And then they cast it as an inverse problem. Now, that is where the inverse problem comes into picture. That the problem is, given the speech signal, find out what the underlying phoneme is. So now how do they do that? They do it by modeling this entire system using existing math. For instance, the speech community was modeling this entire system as differential equations. Okay. And find its parameters. There are lots of parameter estimation techniques. So basically, they cast this problem as, okay, I'm given some speech signal. Let me try to use some physics of the problem and try to estimate what the underlying system is, such that if I'm given a speech signal, I can go back to that abstract concept called phoneme. So you can see a similar thing with the images also, right? I mean, the classical image processing people, if they wanted to find out gender, okay, from an image. So what they used to do is, and let me take that another example of image, right? So you have image to, let's say, object identity. Okay. So what sort of an object is it is what I need to find out given the image. So what do you do is that take the image. Okay. So now model object identity as, let's say, it's a house. If I see a rectangle plus a triangle at the top, okay, and then some regular objects, regular shapes, and so on. So what do? I come up with processing methods, right? That would find out. So basically, what happens is there's this function. So this function that they do is they first find out. So rectangle extractor, there is something called, just extract the rectangle and see where is it. And then you do a triangle extraction. Okay. Then you have some sort of, object location detection and so on, and try to do this and combine all this to come up with some object identity or regular shape. Now that is how people used to attempt these problems. As I said, this is classical speech processing. This is classical image processing, and you can imagine the same thing, right? In NLP also, you have documents to, you need spam or no spam, email spam or no spam problem, right? So what people used to do is, just identify some spam words. Okay. So this count the frequency of spam words and so on. So now you do this and try to find a relationship between the number of spam words and the frequency of occurrence and their position, etc., and then mark it to some identity. So you understood, right? So basically, if I have to trace back to what we discussed so far, what we are actually interested in is, given pairs of observations or elements from two particular sets, we are interested in finding out what the underlying relationship between the elements of those two sets are. Okay. Now, in classical settings, where the relationship between them can be estimated using existing mathematical tools, now you can try to find out how the relationships are. I mean, don't ask me how to do it. I mean, that's an entire branch in mathematics by itself, but you can do it. But now the problem arises where the relation or the function that we are trying to learn between the domain and range do not adhere with the existing mathematical tools. Okay. Now I gave you examples of this machine learning. So why does this happen? This happens typically where the elements of the domain set are measurable, okay, and observed, but the elements of the range set, okay, are very abstract and they are not measurable things. So now how do you solve such problems is the question. As I said, classically what people used to do is to try to use existing mathematical techniques and then find that relationship. But unfortunately, all these attempts, right? I mean, before people started using the probability theory or statistics as a tool to model these relations, none of these things were usable, right? I mean, you didn't have a good speech recognition system, you didn't have an image recognition system, didn't have a good NLP system, because all the techniques that were there were simply estimating wrong functions. That's all. Okay, none of the functions that you estimate. What happens if you have suppose you have this particular way to find out what a house is, right? So what if you have a house which is a modern building, right? That does not have a triangle at the top, something like this. What do you do it? What if it is disoriented? Similar questions can be asked for every system here. A speech signal. Suppose you model something. Somebody comes and the voice changes. You have modeled it for one particular type of population, and the accent changes. So what happens? Those systems were failing there because the underlying function approximation that we have done there, or the underlying function that they have identified using these methods, are not insight. Okay, so this is the thing, right? So now I think they have convinced you enough in appreciating the fact that you need, the existing mathematical tools do not work out. You need another uh, maybe a way or branch of mathematics, right? Which would try to address these kinds of problems where you still want to approximate functions between two sets, but the relationship between the domain and the range do not adhere to existing tools. Number one. The second thing is that the domain set is often measured. The range set is not measured, not measurable. It's a very abstract idea. Now, how do you solve these problems is the question. And that's why probability theory or statistics becomes extremely relevant. I'll tell you what is the underlying paradigm of solving these problems from a probability theory perspective in a while. Okay, so I'll stop here for a while and take questions. Aviroop?
Yes, sir. The example which you just gave, that using traditional techniques, like suppose, the speech example which you gave, that suppose it has been modeled using for a certain set of population, it is not going to work with a different population if it has been modeled with the classical techniques. But even with modern machine learning techniques, we have observed the same behavior. Like if a model has been
Agreed.
trained,
Agreed.
yeah,
I'm not disagreeing at all. But the thing is, overall, right, empirically, the statistics-based method have given you much, much better performance compared to these things. I'm not saying that this is, as people keep saying, no, all models are wrong. So all models are wrong, but some are useful. So these have become more useful, right? More mainstream, more useful. If you have any metric that would measure the goodness of these functions, okay, which is the performance metrics, the functions that people have found out using statistical tools have shown better performance in terms of those metrics compared to classical techniques. That's all.
thank you.
Yeah, but I'm not saying that, okay, the statistics would solve the entire problem. It will give you the perfect function that is approximated. That's not what it is. But as I said, if you take any metric, we have seen this, right? What the commercially available techniques do, right? All our phones have face recognizers and they do fairly well. There are problems, of course, but they do fairly well. All of them are running on ML, right? So, suppose you want to use classical techniques to do it, the generalization capability is rather poor for them. Okay, Arijit?
Sir, just the assumption I made, the example you gave for image classification, like a house or maybe spam, no spam, did it fail because it is more of a rule-based system than ML? Because we are directly identifying whether there is a rectangle or not, whether there is a
Exactly.
square or
Yeah,
not.
that's what I told you, right? What do you
Yeah,
mean by rule-based? Uh, what do you mean by rule-based system? By rule-based system, I mean that you have found that approximated that underlying function using some rules,
correct.
right? And those rules are not again, let's not call them rules. See, one other suggestion or rather request that I have is, as we'll be moving like ahead in the classes, please, okay, two things. One, don't try to force fit your already existing terminologies and knowledge in the class. Okay. Because what happens is, I want to build it brick by brick. And at the end of this course, I want to start using, my language, which is the language of ML community. So please try to use the definitions and the techniques that we have discussed in the class as much as possible. That's one thing. The other request that I have, maybe it's too early for a test, but suppose I'm teaching you, let's say, adversarial networks or diffusions. Please don't ask questions on things that I have not covered in the class. Okay, so because what happens is, I'm sure that what happens is in a large class like this, it will be too heterogeneous. You see, so some of you might find some topics trivial. Some of you might find some uh, novelty there in some topics that I'll be teaching. So I have to cater to the average population, you see. So that's why I will cater my lectures that way. But I do, encourage and request you to ask as many questions as possible. But please don't ask me questions on topics that I have rather not covered yet, right? Or rather going to cover later. And also ask as much as possible, use the terminologies that have been developed in the class. Okay, for instance, the reason I remembered all this is, again, nothing particular to you, Arijit, because I just remember, I anyway had to say this because it came up, I just said. For instance, see, there is no rule here. We have been talking about functions, define what functions are. Okay, so what we are doing here in the classical techniques is that we are learning these functions, or rather we are finding out these. I've never defined this word learning, I'm sorry. So we are finding out these functions, right, using pairs of observations. Now, why do they fail is because the function that we have thought that is the correct function is not the correct. Now, there have been enormous amounts of sense is that okay, somebody said that no, if you want to look at human faces, don't look at these rectangles. In fact, you can go even one step below, okay, where see, what do you mean by a rectangle? I just took this as granted. What do you mean by rectangle? Rectangle is you should have four line segments that are perpendicular to each other and so on. So now how do you find out perpendicular line segments? You have to do what is called as edge detection there, right? Given an image, you'll have to detect the edges. And what if there are multiple edges in the image? How do you deal with it? And so on. And that's why you have these classical image processing techniques, right? Where people look at Sobel filters, different kinds of operators to do edge reduction, and then came these wavelet transforms, etc. So basically, they are asking this fundamental question, right? What is the underlying function that I have to find such that I can relate these two sets that I have at the hand? And because these functions that people have come up with, they are not correct in the sense that they don't predict the correct element in the range set, they are failing. Okay. Now the bigger question is, what other way can one think of when we need to relate these two sets? That is the question. And we'll answer in a while. Okay, Shivam.
Yes, sir. I think you have partially answered to my question, but yeah, again, to understand when we do a function approximation for any particular input, how do we come to a point like we do an experiment and we say that, okay, this function is not working well for this particular input, and we try to increase the complexity by increasing the number of parameters or trying out different approach. But is there any initial study which shows that it's a good start that we should take these number of parameters and try this particular approximation technique for this particular input, or it's just on the trial basis we do?
Yeah, see, that is more of, there is no, there are a few techniques, right, where, okay, there are, see, for instance, neural networks is one large class of functions that you can try out, which are universal function approximators, see, right? So that is why neural networks are so popular. We'll come to that in a while. So why are neural networks so popular is because the functions that these neural networks approximate, right, are a large class of functions. So now instead of trying out different, so let's say you try out a parabola, you try a third degree polynomial, you try an nth degree polynomial, etc. These neural networks are class of functions that can approximate any function to arbitrary closeness. So that's why you can try neural networks. In fact, that is the reason why they are so popular these days, right? They are universal approximators. Yeah. Okay, so basically, yeah. So the motivation is that, right? When you cannot have uh, like off-the-shelf functions, or rather classical functions that would relate these two sets, you need a different kind of paradigm to model these two, and that's why probability theory becomes a handy thing. In fact, I should tell you something. So it was mid 1980s. People were trying to solve this speech recognition problem, and a lot of speech scientists they used to model. Okay, in fact they used to model the entire vocal apparatus as concatenation of several waveguides. So waveguides, you know what waveguides are, right? They are physical cavities where electromagnetic waves travel. They used to model the entire the vocal apparatus starting from lungs to mouth as concatenation of several waveguides with different diameters and lengths. So now when the shape of the wavegate changes, right, the way the wave propagation happens through that changes. So those were being modeled as several differential equations with several initial conditions and so on. People have spent decades doing this. Now, the idea was that, okay, if you can model those things using physics, then you know what sound produces what sort of a signal and so on. But in I think 19 late 1980, I think it's either IBM or Bell Labs. I don't remember which one of it. They demonstrated that using statistical methods, those days they were hidden Markovian models, which are nothing but ML models, right? I mean, using statistical methods, they actually demonstrated they cracked the problem of isolated word recognition, where it's not speech recognition. If you say an isolated word with limited vocabulary, they could identify that. Okay, so people from this classical physics, right, they got so irritated that they said that all that you are doing is modeling your ignorance. This was actually said, this is documented. They said that, oh, because you don't know how speech signal is related to phoneme and you cannot use the first principles in physics, you are simply, modeling the ignorance that you have. And these things were actually called ignorance models those days. And people were very against these kinds of statistical models. But come 2010s, right, we have seen that these kinds of problems can be very easily modeled using statistics and probabilistic methods. Okay. Okay. So I think let us take a short break. It is 10:40 now in my clock. Let's get back at 11 a.m. So what we will do next is I'll tell you like how is this problem solved using the probabilistic methods, and we'll start defining what probability spaces are and what a probability measure is and distribution functions and so on. Okay. So we are resuming in about 18 to 20 minutes. Okay. See you in a while. Hello, shall we resume?
Yes, sir.
Sure, sir.
Okay, so yeah, so we were talking about function approximation. So we want to find functions, right? Given pairs of elements from the domain and range, and we saw that in some of the scenarios, finding out these relationships are non-trivial. So need different kinds of approach for that. So with this motivation, right? So what is done in this branch called the probability theory? The first observation that is done here, I mean, or rather, the first assumption that is made is that vaguely, right? So what happens is lot of human decisions. I don't have to write that. So basically, what is said is allow uncertainty by construction. Okay, so what do I mean by this? Now, this is actually a striking difference between the deterministic way of looking at things and probabilistic way of looking at things. Is that so? In probability theory, right? The models and the ideas are built by inherently allowing uncertainty in all your functions. What do you mean by that? See, look at this. Suppose we want to solve this problem, right? This problem of gender, okay, given a picture. Now, I don't have to tell you, so given every picture, I don't have to tell you whether this picture belongs to a man or a woman, right? Most of the times, our job will be done if I tell you that, look, this picture has about 70% of chance of belonging to a man. And we are okay with it, right? And we'll go ahead with those decisions, isn't it? So another example that can be given is if you look at this emotion as well. So instead of saying that this particular document correspond to one of these emotions, what if I tell you that these documents, they okay, given a particular document, I'll say that okay, this document has 30% chance of being sad and 20% chance of being angry, 40% chance of being happy, and so on. That's enough for most of the tasks that we are supposed to do. So basically, this is the idea that saying that, I mean, observing that uncertainty is okay, right? I mean, basically, so the functions, okay, that we are interested in, which are mappings from the range and the mappings from domain to the range, okay, can possess uncertainties. See, now I think this nomenclature makes sense, right? Prediction. So what you are actually doing is, given a particular element in the domain, what you are telling me is that you are telling me what is the chance of that particular element from the domain, okay, maps to different elements in the range. See the point? Sorry, I was muted. I didn't notice that. Okay, so what I'm saying here is that in probability theory, inherently what is done is the functions that we are trying to learn between two sets, right? They can possess uncertainties by construction. Now, why is this important, or why is this a good thing, is because, as I said, if you allow for uncertainties, right, then what happens is, so uncertainties, allowing for uncertainties, one makes function learning easier. It makes the function learning little feasible, right? Because see, you are if you are giving me more freedom, it's like actually giving the model, I mean, or rather the paradigm more freedom, in the sense that I don't care if you are going to tell me what exactly is the element from the range set that gets mapped to this particular element in the domain set. But I only care whether, I mean, if you tell me what are the chances of this particular member in the domain of getting mapped to a particular member in the range set. So now, I mean, one might think that, okay, I mean, if you do not have I mean, if this uncertainty is there inherently in the model, it can be a negative thing, right? Because if I mean, decisions are deterministically taken. I mean, either you go somewhere, not go somewhere, either you eat something, not eat something. How can I have an uncertainty associated with my decision? It turns out that these functions, and in a lot of the use cases, as I said, it is okay if I give you some odds of this particular member in the domain set getting back to different members in the range set. And I gave you examples on that. For this male-female classification task, or rather mapping task, it's enough if I tell you that, okay, this picture has 70% of chance of belonging to a male. A lot of times what happens is we take chances and risks in life, right? I mean, that is the idea. So you inherently allow uncertainties by construction in the model. You have uncertainties, makes function learning feasible. This is one thing. The other thing that is relevant to this particular course is that if you allow uncertainties, right, this will help creativity. Yeah, it is too philosophical, but think about it. I mean, I'll concretize all these ideas in a while mathematically. But think about it. If we are set on stone, right? If we are deterministic about everything that we do, we don't take risk, as they say. Uh, then you are stuck. You can't be creative if you don't take risk. So creativity. See, for instance, right? When people, when artists write portraits, okay, of people or landscapes that do not exist. What's actually happening is that there is a certain their model of human faces, right? That has a certain uncertainty associated with it. If without that uncertainty that is associated with that, there is no way that this artist is creating a new image, or rather new picture of a human being that does not exist. You understand? So now, if the model inherently, or rather the function or the paradigm allows for uncertainty by construction, it one makes this function learning feasible because there are more degrees of freedom. Okay, and two, it will help creativity, and that's why, right? I mean, generative modeling was possible only through probabilistic paradigms. I will define all this concretely, but think about it. Now, all the while, the problem was that if you are given elements from the domain and the range set, you were to find a function that would map every element in the domain to every element in the range set. Now, if you allow uncertainty, what happens is that you can create more elements from the domain set, and you can create more elements from the range set. That is what generative modeling is all about, right? At some level. So this is what it is. So this is the paradigm where the function learning, right, and the approximation that you do for these functions, you allow for uncertainty, the presence of uncertainty by construction. Okay. Okay. So any questions on this before we concretize these ideas? So what do I mean by allowing uncertainty? How do you do it actually is something that I'm going to talk about in a while. But yeah, before that, in the philosophical idea, any questions?
Sir, here domain range means the input values.
Please raise the hands before you talk. Okay, I'll call out your names. Yes, Karthik.
So previously we used to say in functions some exceptions, right? Not uncertainties, right? Like generally.
No. See, mathematically looking at it, there is nothing called exception. See, there is a domain set, there is a range set, and there is a function that maps elements from here to elements from there.
Okay.
So there's no idea of exception, right, in deterministic function learning.
Okay. Yeah.
Isn't it? So like, F equal to MA, F equal to MA, that's all. There is no exception per se. Right?
Oh yeah, there can be scenarios like what we say, right? When F equal to MA, but given that mass is constant. If mass is not constant, that's an exception to this. So something like that.
Well, it's not really, because see, if you make mass not a constant or whatever the conditions are, then the domain and the range set completely changes. You see, as far as the domain and ranges are fixed, right? It's a deterministic function. No, there is no inherent uncertainty in the model per se or the function.
Okay, sure.
Right? Yeah. Aditya.
Sir, one rather comment, not a question, is that if there is an inherent uncertainty in the system, we cannot use these kind of systems to make any control decisions or any such decisions. Is that correct?
That is why, right now, people are skeptic about using these chat GPTs for all this. See, why do you think people are talking about explainability and safety biases of these systems? Is because they are probabilistically built.
Mm-hmm.
Right? So that's why
Okay.
people are touchy about these things.
Got it. And one more observation on when we say functions, right? Functions are well defined, which maps each input to its outputs, right? If you look at f is equal to ma. So when we talk about these n-dimensional functions with parameters which are in billions, is that something which is I can't visualize that how that function is going to look like.
Well, you can't. I mean, because human beings can't visualize anything beyond 3 dimensions. So you can't visualize those functions. Correct. Yeah. But you can imagine functions, right, that would take billion dimensional vectors as inputs and gives you a scalar. That's very much possible.
Okay.
Right? But of course, those functions cannot be visualized because we can't visualize as human beings beyond 3 dimensions. That's there.
Okay. Sure.
Yeah, so now let's come to this point. That is, how do you allow uncertainty by construction? That's the point. Now, the first thing that is done is, see, remember that we had sets, right? I mean, set A, the way we called it is that, xi, all the observations that we make, x1, x2, all these observations that we make, which are the elements from the domain. The first thing that is done is, now each of these observations are the sets that we look at. Okay. Now there is now these vectors. Let's say that these are some d-dimensional vectors. These can be d-dimensional vectors. Now these are in the probabilistic sense, right? These become what are called as instantiations of a random variable. So these no longer are vectors. Okay. Now they are not just seen as points in some d-dimensional space. They are seen as instantiations of a random variable. Now, what is this random variable business? Now, the way the probability theory structure is the following. So it all starts with probability theory. So it starts with something called a random experiment or a random trial. Please pay some attention here. Okay, so it says that there is a random experiment or a trial that is happening. Okay, why is it called a random experiment? This is one thing that is not well defined in probability theory, right? When there is, what do you mean by random? Nobody knows. But there is an experiment that is happening, and these experiments, they give rise to what is called as outcomes. Basically, these are the outputs or rather outcomes of these random experiments, and these outcomes, okay, are enumerated in a set of outcomes. This is actually critically important that all of you understand. It's not very difficult, but please follow me and understand what it's saying. So it begins with random experiment, and the outcome of the observations of these random experiment is enumerated in a set of outcomes, and this is called the sample space. Don't worry about the terminologies now, but what do you mean by set of outcomes? It is simply enumerating, right? Just listing down all the possible outputs of a random experiment. Now, what is a random experiment? Anything that you want to model, right, now becomes a random experiment. Let me give you an example. Let's take the example of, I don't know why this suddenly gives me some weird shapes. Example, let's say that we have images, right? Okay, so even before coming to that, let's take easy examples. Now, a random experiment can be tossing a coin. I mean, all of you know this. Tossing a coin is a random experiment. Okay. Now, what are the questions that you are interested in? Like, I want to know when I toss the coin 100 times, what are the odds that, like, how many times does the coin turn out to be head or something? Those are the kinds of questions that I'm interested in. But random experiment is simply tossing a coin. Now, what is the sample space here? What are the possible set of outcomes? The possible set of outcomes are head and tail. Okay, assuming that the coin has two faces. This is one example of a random experiment. Now, another example can be like, people can tell me what it is, so you can roll a die, roll an unfaced die. Now, the sample space in that case would be, so 1, 2, whatever possible outcomes that are up to n. So you've got an idea of what is a random experiment, right? I mean, anything, an experiment that is being performed and is called a random experiment. And the possible outcomes of that random experiment is just enlisted in a set, okay, which is called the sample space. Now, when we get to we are not interested in rolling the die or tossing a coin. We are interested in looking at an image and finding out whether it's a man or a woman, right? So now, taking a picture of a person is a random experiment. Can you visualize taking a picture of a person as a random experiment? Let me tell you what I mean by this. Now, imagine that you can there are infinite people that are there, right? And you taking a particular sensor and shining light on a particular person and measuring the reflectance of that particular person becomes a random experiment. Now, what is the sample space? Can somebody tell me what would be the sample space?
The same picture can never repeat twice. So
No. I'm simply asking what is the sample space? Okay, so let me just go back to definition. So what is sample space? Sample space is simply the enumeration of all possible outcomes of a random experiment. Okay. Now, the example, right? In tossing a coin, the head tail are the sample space. In rolling an n-phase die, the 1, 2, 3, etc. n are the sample space. Now, if you take a picture of a person, what is the possible sample space? Yeah, I
All
think if you
persons
were
in the
to
image.
Male, female, and maybe third gender.
All pixel combinations.
Male, female, and third gender.
no, it's not that because I'm talking
All
about
people of
yeah. So it's actually I'll write it as person 1, person 2, person 3, and if there are whatever, right? If you have like let's say 7 billion people in this world, you have 7 billion possible outcomes. Can you see this? So basically, this is the way you are modeling it. You understand? So now the random experiment that is happening is simply taking a picture, okay, of a person is a random experiment. It's simply like rolling a die. I mean, when I see, this is the worldview that you should slowly develop when you are dealing with machine learning. That reading an image from one of these OpenCV libraries or something is nothing different than tossing a coin in the probabilistic sense of words. Okay. So now that's why I wrote the sample space, right? I mean, there are these many people, every person now becomes the sample space. And similarly, you can imagine, right? I mean, now suppose I'm recording speech. Recording the speech signal. What happens is that every possible sentences that everybody in this world can talk of becomes a sample space. You understand? Okay. Any questions on what constitutes a random experiment and what a sample space is? Okay. Now what happens is that when we measure, right? I mean, when we have a sensor and we or we have a condenser microphone, we measure it. What we get to measure are not the elements of sample space. So let me write that. So elements, maybe before coming there, let me just define the probability measure. Okay, so this is the sample space. Now, so now this is a set. Okay, now let me give you an example. Let's say that I have set of real numbers, which are, yeah, simply take set of real numbers, write them. Set of real numbers. Okay, call it R. Now, I take a subset. Let me call it used this already. A lot of notations very quickly. So let me call it A1 is a subset of real numbers. Okay, and A2 is another subset of real numbers. So for example, this can be 0 to 2. Okay, this can be 3 to 8. These are two subsets of real numbers, right? See, my interest now is I want to compare these two sets. How do I compare these two sets? Okay, so let's say that the intent to compare A1 and A2, which are both subsets of R. I tell you what is the relevance of this with sample space in a while, but yeah. So let me take some like opinions here. If I have subsets of real numbers, how do I compare subsets of real numbers?
Maybe what is the common numbers between two sets?
Okay, so how does that tell me how I mean anything about these two sets? Okay, so I'll tell you what do I mean by compare, and I want to ask questions like which one is bigger, right, or smaller, something of this sort. So how do I do that? I think people have raised their hands. Harsha.
Yes, sir. So one way to compare is Like if you're able to map each element in this set to another element in the other set we are comparing, and if we are able to map,
I can't. No, I can't, because here I can't find a function that would. Okay, are you saying that I have to find a function that would map elements in set A1 to A2? See, again, when I say compare, right? I mean, please take this the question. I want to know which one is bigger and which one is smaller. You all know the answer to this question, but I just want to hear from you. Yeah, Nirmit?
Finding the cardinality of the sets.
Both of these sets have infinite cardinality, no? These are subsets of real numbers. Cardinality of both of these are infinity, isn't it? You see that in the myth? Because
Yes.
these are subsets of real numbers. So cardinality won't give you anything. If it's a discrete set, of course, but it's a subset of real numbers. No, cardinality won't help. Vivek? Vivek? Okay, Balaji?
So we can find like mean, median, something like that.
How does taking mean tell you which one is bigger and which one is smaller?
Like
I mean, there are only, it's a set. You understand that it's a set, no? So there are infinite numbers. So now how do you take mean of infinite numbers? See, there are infinite elements in both of these sets. Does all of you agree with that? You can respond with a emoji or something, right? Does all of you agree that there are infinite numbers in both these sets? The cardinality of both these sets are infinity. So the average doesn't make sense here. I just want to know if you can tell me which one is bigger. Right, that's all. Maybe I'll make the question easier, right? To tell me which one is bigger. Okay. So let's ask this question. Which one is bigger in these two sets? Aditya. And by the way, when I ask you a question, right? And when you raise your hands to answer, I would randomly call out names. Okay, so please don't take it otherwise. When I ask you, if there are any questions, then I'll go one by one. When I ask you questions, then I just take random order. Okay, so here is the question. The question is, which one of these two is bigger? Abhirup.
If we apply the length measured, then the set on the right hand side seems to be bigger.
Okay, what can you expand that? Okay, let's say use this word measured.
Yeah.
What do you mean by that? That's exactly where I'm coming to.
Yeah. So
you said length measure. What is length measure?
Length measure is a function which maps the number of sigma algebras in a set to a number.
That you seem to know things. So now I didn't talk about sigma algebra yet. Okay. So what is a measure? So basically what he is saying is just look at the length of these two sets. Okay, so now you represent these two these two sets on a number line. So this is 0 to 2 and this is 3 to 8. Okay, now this line has a higher length compared to this line, correct? Does all of you agree? All of you agree with this, right? So basically
Yes, sir.
what we are saying is that associate, how do you generalize this idea? Associate, okay, a scalar positive function, a non-zero function, with every subset of R. Basically, given a subset A of R, what I do is I take that subset and associate that with some number, okay, which I call as mu A, okay, which is a positive real number between 0 and that. It's simply a positive real number. Okay, I can actually say it as belong to R plus. confuse you with notation. It's a non-zero real number. Non-zero. It can be zero also. Say it as it's a non-negative real number. Yeah, that's what it is. You understand? So what we are doing here is that for every subset of real numbers, we are associating a non-negative real number. Okay, which I call as, and by the way, this is defined as measure of A. Do you understand? Now, basically, let's abstract out. So we are given a set, okay, which is set of real numbers, and we are taking subsets of this set, and corresponding to each of the subset of this set, I associate a non-negative number and I call it the measure. Does it make sense? So basically, what does measure do is that a measure is basically a function that will take a subset of a given set, okay, and maps it to non-negative real numbers. Do you understand? So this is a measure. So now why is this important is that given any subset of a given set, okay, now you can compare sets based on their corresponding measure. This facilitates comparison for subsets. Okay. Let me give you another example. Let's say that our set is set of R2, which are two-dimensional vectors. Okay. What can be so, which means that an element here, right? An element in R2 is represented as x1 comma y1, or let me call it x1 comma x2, which is I write it as capital X, which is x1 comma x2. Okay, this is an element. Now suppose I give you, okay, so now tell me a measure that you know of that is defined on R2. The measure on R2. You people already know this.
Root of x1 square plus x2 square.
Come again.
Magnitude root of x1 square plus x2 square. That can be used to.
Yeah, but that's an element, right? I'm talking about a subset. If I take a subset of R2, okay. See, remember that measures are defined on subsets. See, in R1, what happened? We represented every subset as a line segment. Okay. So now if I write R2, how are each subsets represented here?
Areas.
How are each subsets represented?
Rectangles.
They need not be rectangles. Yeah, there can be, it can be any irregular shape, it doesn't matter. But for now, yeah. So this is a subset, right? A subset in R2. Okay. Now, what can be a measure that you already know on subsets of R2? Area measure. You understand? So every subset has a measure called area now. Okay. Now, if you extend this to a d-dimensional real space, what is the measure?
Volumes.
They're volumes, right? I mean, they're hyper volumes. You can't call them volumes, they're hyper volumes. So this measure that we know of, right, which is, which is length in one dimension, area in two dimension, and hyper volumes in three dimension, it has a name. Do you know what the name for this measure is? Does anybody know the name of this measure? See, there can be, this is not the only measure that you can have. You see, given subsets of any sets, you can come up with any measure. And there's a definition of measure, right? Okay, that if you have a set with zero cardinality, the measure has to be zero. So if you have two non-overlapping subsets, the measures have to add up. Yeah, the measures of the individual subsets has to be equal to the measure of the union of those subsets. Okay, so these are some of the properties that the measure should have. But anyway, you can come up with multiple measures. Actually, you can come up with your own measure and give it your name. Doesn't matter as long as these properties are satisfied. But the usual length, area, volume measures that we know of, right? That we use, that we have been using since class 5. There's a name for this measure. Do you know what the name for this measure is?
Norm?
No, these are called Lebesgue measures. I don't know why his name is spelled like this, but yeah. So this is called Lebesgue measure. So all the length, area, etc. that we do in Cartesian or rather Euclidean spaces, right? D-dimensional Euclidean spaces, they are called Lebesgue measures. So the length, area, and volume measures. Is this idea clear? Why am I talking about measures here? There's a reason for it. Just give me a while. I'll come to that. So now you understood what measures are, right? So basically what I'm doing is that I'm given a set. Okay. I'm constructing the subsets of that particular set. Okay. Now for every subset that I'm constructing on this particular set, I'm associating a number with it. And that number is what I'm calling as a measure. And we just saw an example of a measure in D-dimensional Euclidean spaces, and we called it as Lebesgue measure. Any questions so far? Hello, am I audible? Are you there?
Yes, sir.
Okay. Yeah, there are a few questions. Lokesh Kumar.
Yeah, sir, is there a reason why the measure has to be a positive?
Good question. It's by definition. See, the thing is, because we perceive measures as something that is that we can compare. So we can't compare negative numbers. You see, we can only compare positive numbers. See, if you perceive these things as lengths, there cannot be negative length.
Okay.
Yeah, I mean it's only a convenient definition convenience. So the way the measures are defined, they have to be non-negative. Yeah.
Okay.
Yeah. But by the way, there are lots of measures. Lebesgue measure is only one of the so many measures that people have come up with on real numbers. But yeah, so Lebesgue measure is one of such measures. There are other measures like Henry measures, Riemann measures, and so on. But yeah, so the usual measures that we look at, right, they are lengths and areas and volumes. They're all Lebesgue measures. Okay. Any other questions on this? I mean, what constitutes a measure? So again, I'm defining, right? I mean, it's basically a function, a set function that would take subsets of a given set and maps it to a non-negative real number, such that there are some properties. I'm not going into details. One property is that it has to be, see, every measure by construction, by definition, has to be non-negative. For any set, it has to be greater than or equal to 0. The other thing is measure on the null set has to be 0. Okay, and the measure on union of two sets has to be equal to the individual measures if the intersection is null. These are some of the properties. I mean, as long as you can come up with a function that would adhere to these properties, you can name it, you can give it your name and call it your measure. Okay, so this is the length measure. Okay, so now why did I talk about this? Remember that we were looking at random experiments, okay, and we are looking at outcomes. Now, what are outcomes? So we do have a set here, okay, which is called the set of all possible outcomes of a random experiment, and we call that the sample space. Okay, because we have a set. So we have this set, which is sample space. Okay, what is that? That's a collection of all possible outcomes of a random experiment. right? We have a sample space. We can now create subsets of this sample space, right? Now let F denote the subsets, set of subsets actually. Make it the set of subsets. Do you understand what I'm talking about? Again, you can go back to your examples, right? If you are rolling a die, you can take 1, 3, 4, 5 as one subset of the sample space. If you are looking at tossing a coin, you can head, tail, whatever, right? They are subsets of omega. I mean, this is omega by the way. And if you are looking at pictures, then if you take pictures of several, so some set of human beings, right? That is a subset of this particular set, and the F denotes the collection of all such subsets of the sample space. Is this clear? See, just like we had the line segments, right, which are pieces of number line, real line. So you have subsets of the sample space, okay, which is a set. Okay. Now we have a set and we have a subset. Because we have a subset and a subset, we can define a measure on it. Correct? So now define a measure. A measure P. Okay. Actually term the probability measure. Okay. On every subset, every element of the subset of sample space. So now given any element that is a subset of the sample space, then I will define a measure on top of it. Okay. And this, right, is defined as a measure that is between 0 and 1. See, unlike the Lebesgue measure that can take any non-negative value, the probability measure, okay, can only take values between 0 and 1. So now you might have this question, right? Why did we do it this way? Did it this way because, as I said, remember the goal is to associate uncertainty in the entire modeling process. You see, okay? And how do you do that? This is one of the ways of doing it. Now you say that, okay, everything that you observe is an outcome of a random experiment, and every subset that you observe, okay, or every outcome, every subset that you observe of the outcome of the random experiment that you are doing, now is associated with a particular measure, okay, which is lower and upper bounded between 0 and 1. So now you interpret these values as the amount. So basically this measure, right, the probability measure, that's such nuisance. The probability measure, okay, can be interpreted. So just like you interpret the Lebesgue measure as length, okay, interpreted as the uncertainty associated with a subset A, which is a subset of sample space. Do you understand? Now, if you go to this example of looking at the speech and the images that we have as the elements of sample space, you can imagine if you take any subset of the sample space, there is an inherent measure, right, that is associated with this particular subset that would quantify the uncertainty that is interpreted as an uncertainty associated with this particular subset. Does it make sense? See, you should see probability, right, just as you see length on a real line. So what is length? Let me write that. So length and areas on RR2, right, is exactly equivalent to probability on sample spaces. Can you see this point? Now, see, I just made this statement, right, that remember that we are interested in doing this, function learning business. And we came up with this paradigm called probability theory. So what is basically being done is you model, or rather you see everything that you have, right, as, see, okay, so let me go back. I think it's a very nice analogy here. See, here when we said that we have pairs of observations, right, that are coming from two sets. Similarly, the set of the domain that we talk of for function approximation now becomes the elements of sample space. Okay, and just like you associate lengths with the subsets of real numbers, you associate another measure called probability measure that would tell you, that will not give you the length of these sets, okay, or subsets. This will tell you how certain or uncertain that particular set is. Do you see this point? Any questions so far? There is one other piece, that I have to talk about, which is the idea of random variable and distribution functions. We'll see that, and then we'll stop this class, because from next class I can start formulating what generative modeling is using these terminologies. But yeah, any questions so far? This is actually bare bone fundamentals for studying any of the ML. Okay, so let us ensure that you people understand what I'm talking about. Any questions here?
Sir, if we take the set of all subsets of a set and assign a probability uncertainty for each of those subsets, is that what we are talking about?
Correct.
Then that's called a sigma algebra, right?
That's a sigma algebra, of course. F is a sigma algebra, no? Okay. F is actually a sigma algebra.
Sigma algebra. Okay.
That's also called the event set. See, because I'm not teaching probability theory, I'm not going deep into this. First course on probability theory should start from this. So what you said is correct. F is a sigma algebra, and the measures are only defined on sigma algebra. This is the sigma algebra defined on top of or obtained from the sample space. That's correct.
Okay. Okay.
Harish Gautam. See, I don't want you to overburden with terminologies. You see, I'm only defining what is absolutely necessary. Harish Gautam.
Sir, is sample space same as domain?
Not yet. Okay, not yet. I would not say that because hold on to that question. That's a very good question. I'll come to that in a while. For now, I would say no, they're not exactly the same. See, because look at this. See, if we are looking at taking the picture of a person as the random experiment, and we are looking at every person as the outcome, right? Then where is the domain of the functions that we actually talk of? See, because what we measure, I mean, not the measure theory measure, I mean English measure, what we observe, let's say what I observe are real numbers. Okay. The elements of the sample space are not real numbers. Can you see that? Elements of the sample space are persons, or rather, sentences, or they are documents, which are not real numbers. Do you see that?
Yeah.
So now the biggest challenge is, which I'll talk about in a while, is that you need a mechanism where you convert the probability measure, right, into a space which you can, which you can imbibe some other sort of a measure. In fact, where you can use level measures. And that's why random variable comes into picture. I'll talk about it in a while, but don't think of the outcomes of a sample space as domains yet. There is a relationship between them, but they're not exactly the same. Okay. That's a very good question, by the way. Nice observation. Yeah, Aviroop.
Yeah, so how do we extend this notion? Like you gave the example that, if we consider the set of all people as the set of sample space, and then if we are assigning uncertainties to certain sets of people,
all subsets, all possible subsets.
All possible subsets of people.
Exactly. Yeah. So you take any possible subset, it can be a singleton also, in the sense that you can take a particular person and that particular person which happens to be a subset also has a measure associated with it.
Yeah.
Get it?
So so my question is that how is this notion is going to help us to figure out whether that particular person is a male or female? I mean,
well, you have to wait.
okay.
That's a good question. We'll see that. We'll see that. Yeah. Yeah, Arijit?
Sir, what I understood, the complete theory is based on the correctness of the sample space, right? Now,
No, hold on. No, don't jump. What do you mean by correctness of sample space? I never defined that.
I mean to say that suppose the random experiment I am doing, defining a sample space, and from there we are taking the subsets, and all this theory is based on that. Is not it? Now, suppose if we don't know the sample space, or suppose we are talking about the planet in the universe, multiple planets. So on those cases, it is very tough to define a complete sample space, right? So on those cases, is there a parallel line of probability?
Okay. See, in fact, we never go to sample space because of this exact reason. We never care about sample spaces. We only work with random variables. Just hold on to that. I'll come to that idea in a while.
Yeah,
okay?
sure.
Yeah. Yeah, Raghavendra?
Yes, so why does it have to include every subset of I mean
definition of measure, right? See,
yeah.
because that's how we defined it, right? I mean, given any subset, it has to assign a value, non-zero value. Because think of, I mean, you look at the Lebesgue measure, right? You take the real line. Given any subset of this, I want to associate a length with it, isn't it? You get it?
Yeah, but it need not be pairs, right? Say, for example, if I consider 0, 2, 3, I mean, does it also work on that? Because so now you have three elements in that.
No. Oh, okay. See, it's not a subset, you see. See, when you write, what do you mean by 0, 2, 3? Are you talking about 3-element subset?
Yes.
See, 0, 2, 3 is not a subset of R. You should always remember that we are talking about the subset of a given particular set. 0, 2, 3 is not a subset of R. Do you see that?
It is, right? Or
is it? 0, 2, 3, is it a subset of R? The discrete set. I mean, I think is it a subset of R? Singleton, right? I mean, if you take two elements, you are talking about this, correct? See, note that I'm not putting square brackets here. If I put a square bracket, then it's a subset. Now, if I write 0, 2, 3, is it a subset? Let me just confirm. Yeah, set of naturals is a subset of R. Okay, yeah, fine. Then it's a subset of R. Okay, it's a valid subset of R. That also has a measure. In fact, the Lebesgue measure of a discrete subset of R is 0. Okay, it's like this, right? I mean, if you write this 0, 2, 3, you're actually asking me what is the length of these 3 points. Do you see that?
yeah, so that's where I'm confused. So when I say a
It's
measure
0.
of A,
It's
so
0.
measure of A, so I mean, what all do we really consider in that A? And also, if you
It can
scroll
be any
down below,
subset. See, it can be any subset. See, any subset, right, from the set of real numbers has an associate measure. But Lebesgue measure of this particular singleton or like discrete subsets of R is 0. That's all.
yeah, if you come to this 2D picture, right? I mean, there we said that.
Yeah, if you take the measure, if you take the area of a line, it is 0.
Yeah, but in let's stay with this example. So when we say that element x1, x2, right? I mean, it's again a point in
Yeah. That's why I said no. Measure is defined on subsets of R2. This is not a subset of. It can be a subset of R2, but this is again a set that has zero measure. You get it? This particular singleton has zero measure.
Any example where the measure is non-zero?
This thing, no, this rectangle.
Okay, so we choose a region in the space and then
R2,
we associate.
Exactly. Yeah. In R2, you take a subset of R2. Okay. So it's like this. Okay, let me write it down. So this particular set. One point, 1,2. This thing is 1 point, comma 4,3. This has a non-zero measure. Understand?
Yeah, because it defines a rectangle, right?
Exactly.
And if you go back again to the one-dimensional case, I think even there we can say the same stuff, right? So length is a measure when we define it over a range.
No, see, that's what I'm saying. See, if you take a subset, you take any subset, the way the measure is defined, it doesn't tell you what subset you have to take. You take a point here, you take 3 points here, okay? That's also a subset of R. Now the question is, what is the measure of that particular subset? The measure of that particular subset is 0, that's all. It does have a measure, but it has 0 measure.
So you need a kind of an interval to get a non-zero measure.
Lebesgue measure. Lebesgue measure.
Okay.
Yeah. Lebesgue measure is defined that way.
With an interval, right?
In fact, the definition of Lebesgue measure is, so if you have a subset of R, right, which is a closed subset of R, then the absolute difference between the final element and the initial element is the definition of Lebesgue measure. Okay.
Okay.
It is an interval, right? So that's why if you take a discrete set, the measure is 0.
So if you take individual points, if you take individual points, the measure is 0. But if you take an interval, then we have a valid measure. A non-zero measure.
Non-zero measure, exactly. Yeah. See, that is why it's a very good question. See, if you have a continuous random variable or a continuous sample space, the probability measure for a particular point is 0. For instance, if we are looking at this particular example, right, of people, the probability associated with one particular person is 0. You see that? It's actually like, finding the Lebesgue measure of a point. It's similar to that. So that's why if you have studied probability theory before, people would say that for a continuous random variable, you should not interpret the probability density function as valid probability measures, because the probability of obtaining a particular point, right, in a continuous sample space is 0. Just like the measure, Lebesgue measure associated with a particular singleton subset of a real number, real set is 0. Anyway, so if you understood it, fine. If you didn't understand that, just ignore it. Okay. I didn't mean to confuse you. Shall we move on? Okay. Now the next question is, now you understood what probability measure is on sample space, right? So the next thing is, see, somebody asked me this question, right? So now what happens is, sample space, rather elements of sample space, are not observed in practice. Because, right, what you see, TIECE, right, or TICE, what is it? TICE. So what I'm saying is, you only get to see the picture of a person, you don't get to see the person. You see what I mean? If you take the elements of sample space, you don't get to see the entire sample space, right? You don't get to or rather, let's say elements of sample space are not observed in practice in its entirety, number one. I mean, I think Arijit asked that question, right? When you don't observe everything, what do you do? The other thing is you don't even get to see the elements of sample space. When you do a measurement, all you get to see is that you measure, or rather, I mean, not measure theory, measure, you observe some real numbers. When you see the speed signal, you are not, the outcome of your random experiment is speech. But what you are measuring is rate of change of pressure as a function of time. Now, how do we deal with it is the question. Somebody also asked me this question, right? Is the domain that we talk of is actually the sample space? No, because what we observe, what we get to measure and observe using equipments, okay, or sensors, are not the elements of sample space. Now, how do we deal with it? Okay, that's a very important question. So for that, what is done is, so define, therefore, define a function, okay, from sample space to some real numbers. So what are we doing here is that, let's say that you have your sample space that are like all persons, okay, or rather you're doing that random experiment where you are looking at all people, okay, that's your sample space. Now I define a function, okay, x is a function, okay, that will take a person, or rather take an element from the sample space which is a person, okay, and map it to some d-dimensional real number. Do you see what is happening? What is happening? Take an element from the sample space, okay, and map it to real numbers. Do you understand? So if you take the example of head and tail, a function that we are talking about will take head and maps it to, I'll have to write it as a function. So 0, the function evaluated at tail is equal to 1. So here I can't write, I mean, the first example, I can't write it this way because every of my element, x of person 1 will now become a d-dimensional vector. I mean, I can't write a d-dimensional real vector. For our convenience, it's actually a p cross q image. Let me write it as p cross q dimensional to make things easier. So every of this entry is a real number. Do you understand what's happening? What's happening is, because the elements of sample space are not observed, okay, you assume that there exists a function that will take elements of sample space and map it to something that we measure or observe. See, this is what we get to measure, right? So what do we get to measure? We get to measure the observe or measure or sense the elements of range space of the function x that would take the elements of sample space and map it to some d-dimensional real space. This is what we get to observe. See, when we have an image, we have p cross q real numbers, right? Every image is a p cross q real number. What is it? The way we should see it from a probability theory perspective is that what is happening is you should have the entire story in your mind. What's happening is somebody is doing a random experiment and there is a sample space. We don't get to see the sample space. But there is another function that is taking the elements of sample space and mapping it to real numbers. And these are the real numbers that we get to observe. Does this make sense? And do you know what this function is called? Does anyone know what this function is called?
It's a random variable.
That's the most unfortunate thing that has happened. This function x is called a random variable. the biggest misnomer of all times. This is neither random. Why? Because it's a deterministic function. Right? Nor a variable. Because it is a function. I don't know who named it random variable, but that person has done a big mistake. This is neither a random, this is neither random nor a variable. It's actually a function that is defined between the elements of sample space to real numbers, or like d-dimensional Euclidean space. Make sense? Now, in the deterministic function approximation problems, what we used to call as domain are actually now the elements from the range space of the random variable from the probabilistic standpoint. Can you see that? Now, set of images that we have as data. This is what is called as a data. Okay, set of images which is data are elements from the range space of a random variable x, that is mapping this into. Do you see the shift now? In the deterministic function mapping scenario, in the classical scenario, our data was simply points in a PQ dimensional real space. Now, they are still the points in PQ dimensional real space, but they have to be seen as the elements of the range space of an underlying function. Okay, of an underlying function. Oh, I think this works as a pointer. Great. So I serendipitously discovered it. You see? So if I do it below what I want to highlight, no, it'll put that like invisible yellow line behind, but it's okay, I suppose. Yeah, you see? Yeah, I was making a very, very important point here that in the probabilistic way of looking at things, the data or the images that you get are just not seen as the elements from a set. Okay, they are seen as the elements of a range set. Okay, and when you talk of range, there is a corresponding domain. And what is that domain that we talk of? The domain is the sample space. Is this idea clear? So every image now, okay, is actually an element from the range space of a function that is called a random variable, which is mapping the elements of sample space to this Euclidean space. Now, do you see why are we doing this? You know, if you can connect the dots, see the idea of identity of a person is associated with the elements of sample space. But what we are getting to measure, right, or see are some real numbers. Now we have to somehow relate these real numbers to the idea of the person, okay, which are elements of sample space. Therefore, we need a connection between the sample space and real numbers, which is provided by this function called random variable. Is this clear? Okay, questions, Raghavendra?
So this is just one function which maps it, right? I mean, there could be many functions or many random variables defined over the same sample space.
Yes,
so
precisely.
And in this example, say for example, the set of persons was our sample space, right?
And you can define multiple random variables on top of it.
Yeah, for example, some gene profile or something of that. So that can also become a random variable.
No. Again, yeah. See, there is no physical connotation to random variables. You see those functions because what you are saying is that what we measure may not be
the picture.
The pixels. Of course,
Yeah,
absolutely.
It could be in a totally different domain.
Absolutely. But you measure the height, weight of that person, that becomes another random variable. Yes.
Okay, it's a mapping from the sample space to real. some real space.
Yes, that's a random variable. Now, what happens is, the next step is, because we have a measure that we have defined on the sample space, right, or the subset of sample space, that measure gets translated, right, into some sort of function under this random variable X also. You see what I'm saying?
Yes.
Under the random variable, the measure that was defined on subset of omega now will be measures that are defined on subsets of R. You get it?
Yes.
That's called an induced measure, and but that measure has a very, very famous name that all of you know of. That is called the cumulative distribution function. The probability measure that gets translated, right, via a random variable, the induced measure that is defined on what is called as Borel sigma algebra or the subsets of R are actually called the probability distribution functions. Now the story is complete. I'll write all that down because you asked, I'm saying the story is that now instead of working with deterministic functions, we work with probability measures. Okay. Now those probability measures get translated into distribution functions under random variables. Now because we get to see random variables, okay, we work with distribution functions. So now the entire story now is that given some elements from the range space of random variable, okay, estimate the underlying distribution function. That is all the machine learning is all about. Be it generative modeling, discriminative modeling. I will connect it to how is it related to general detection, or like even ChatGPT is doing the exact same thing. Given a particular random variable, observations from a particular outcome of a random variable, estimate the underlying distribution function. That is all underlying probability measure actually. I'll come to that in a while. Okay, Sachin.
Yeah, hi sir. So I did not understand this range space. What does this exactly mean?
See, a function has a domain and a range, no?
Correct.
Range is this nothing. This is the domain.
Okay, for this function, this is the domain, and this will be the range space.
Yeah, range is RPQ.
Okay, and it okay.
And in this particular example here, the domain is again this. This is the domain. The range is discrete set of 0, 1.
Okay.
See, what we see are the elements of the range space under this random variable, correct?
Correct.
Aditya?
So we cannot have a random variable which is non-measurable. Is that statement correct?
See, non-measurable in the sense of measurability, right? I mean, you're talking about the measurability of a particular set. Are you talking about that?
Yes, sir.
You can't know because because there is already an underlying measure that is defined on the domain of random variable. Again, please be very, very cognizant of the fact that random variable is a function. So whenever I talk of random variable, it's a function that I'm talking about. Okay. Now, because there is an underlying measure that is defined, that has been defined on the domain of this random variable. Okay. There's always an induced measure that comes with it. And that induced measure itself is called as probability distribution function.
Got it,
See, you
sir.
have defined a probability measure on the sample space already, right?
Mm-hmm.
Because of that, when you define a function on top of that particular set, there's always an induced measure that comes on along with it.
Can we have a set which is non-measurable, meaning there is no
Yes.
measure?
Yes, there can be. I mean, this is like this. It's a topic of its own. There is this branch called measure theory. You should study that. And by the way, if anyone of you is interested in this kind of a treatment, right, there is one very good NPTEL course by Professor Krishna Jagannathan. It's a good friend of mine from IIT Madras. So I think Introduction to Probability for Engineers or something. That's the course name. If you have interest in this kind of treatment of probability theory, please have a look at it. This is the last time that I'll be talking about measures and all this. Okay, the moment we go to distribution functions and density functions, we'll work with density functions. I mean, I just wanted to make the footing solid, right? Because people don't often understand where are this probability density functions coming into picture? Because when you are given some data, what is data? Data is simply some 10,000 images or some documents or some speech signals, etc. The thing is, we talk of probability distribution functions of this particular speech or images or something. What do they even mean? Okay. I always take this one particular, one introductory lecture to ensure that people exactly know what's happening. No, when we talk of probabilities of images, we actually mean that, oh, there is this is the element of a random variable, that's a function. So this random variable has mapped the elements of sample space to this particular real numbers. So now that sample space has a probability measure, and it is that probability that we are talking about. Okay, I just wanted to give that connection, right? Completely. I need 15-20 more minutes to establish that connection before we define what generative modeling is. Shall we do it in next class? Okay. So here is an appeal. While coming to the next class, please look at some of these definitions that I just told you. Okay. And in fact, we didn't cover a lot. I mean, it seems like we did a lot, but we didn't cover a lot. It was some definitions, that's all. Please have a look at them. Okay. And so as I said, no, every class has we have a causality, right? I mean, you have to know what we did in this class to understand what we are going to in the next class. With the next class, we'll go to distribution functions and define what a generative modeling is, and we'll go to the adversarial learning and so on. Okay, that's how the trajectory is. So please come prepared for the next class with some of these basics. Please look at what distribution functions are from this angle, right? What are density functions? How do you define density function, distribution functions on this and so on? Please have a look at it. Okay, I'll not be talking about measure theory anymore. And like if you have any comments, concerns, etc., there's always that like anonymous feedback form where you can go and express your, because this was the first actual class that we had, right? In fact, the second half, the first half was only some introduction. So you can go to that feedback form and let me know what do you think about this, and if you need any particular change, I'll be happy to incorporate them. Okay. So any questions on today's content? Any comments? I think Sachin has something to say. Sachin?
Yes, sir. So just one question in this context of images. So like one image has multiple pixels, right?
Correct.
Now this random variable function, which like takes a sample space element and converts it into this RPQ. So like this random variable will be for the all the pixels of that image, or like is it
Okay. So I think that was apparent anyway. See, we say that RPQ, no? What are these PQ? PQ are the dimensions of the image. So if you're looking at a 400 cross 200 image, P is 400, Q is 300. So basically, we are saying that every image is a point in a 12,000 dimensional space. Okay, and that becomes the range of the random variable. Make sense?
Okay. Yeah.
Okay. Anything with Arijit?
Sir, maybe just a logistic question. The same book, right? Ian Goodfellow, which explains all this theory.
See, this Goodfellow book does not have any of this.
Okay. Okay.
So, see, again, as I said, no, this is not a part of the course because this
Right.
is supposed to be some fundamentals. But as I said, just to ensure that everybody knows what's exactly happening under the hood, I do this. From next class, we'll go to the contents in Goodfellow's book. Okay.
Okay, sure. So
Okay.
any books, if we want to
I
follow
told
along
you,
with your
no,
lectures?
is if you see for this
Okay.
particular treatment of probability theory, you look at Professor Krishna's lectures. This is not needed. I mean, meaning,
Okay.
I mean, if you know this, it's great, right? But this is bare bone fundamentals.
Yes.
After you know this, then we will move on to distribution functions and so on. Huh?
Sure.
Okay. Prasanna? Yeah, class is over. I mean, people can leave if you want. Thank you. Prasanna? So Prasanna, are you there? You want to say something? Perhaps he's not there. Okay. So thank you, everyone. See you next week. Bye bye.
Thank you,
Thank
sir.
you.
Hey, should we create a
you, sir.
WhatsApp group? Should we create a
Hello,
WhatsApp
am I
group?
audible now?
You're
Yes.
audible now. Let me just create a WhatsApp group and send you the link.
Hello.
Go on, Prasanna.
Am I audible?
Yes.
Okay. Yeah. Thank you. I think someone asked the question that if the input is images, then what would be the range? So on continuing on the same question, so what kind of probability measure we should consider in that case? Is it like hypervolume kind of thing?
Yeah, that's the entire question that you ask in machine learning. What is the underlying distribution that defines this particular image space? Nobody knows, no? That's what we model using neural networks, isn't it? You will see
So
that
we
in
try to
that's
find out that probability measure itself.
absolutely, because if you do that, then you have solved the problem, isn't it? Then you know everything about it.
Okay.
The entire
So
machine
when
learning is
PDF
finding out that underlying measure. The entire machine learning is finding out the underlying measure. That's all it is.
Yeah. Okay.
I'll establish that connection in the next class. I wanted to do that in this class itself, but we ran out of time. I underestimated the time that I would take to do all this. So I'll do it in the next class. Please, maybe you can ask that question, but anyway, I'll start the next class with the answer to that question. Yeah. I was asking if we have to create this thing, WhatsApp group.
I think Shivam has created one already, sir, including you.
Oh, that group is there. I think everybody is not there in that group. So maybe Shivam, can you put it in that Teams group? I think he is not there.
Yes, sir. I'll ping the link on the Teams group.
Please do it, huh?
Yes.
Yeah, so that everybody is there. I think that's the easiest way to communicate. You see, some resources, etc., we can quickly communicate and so on.
Yes, sir. But it might have a mix of people who have not opted for the course. Not sure.
It's okay.
Okay.
We are not, doing some dark state activities here. So fine. They drop out. Yeah. And then you can say that the people who are not enrolled in the course may opt out.
Okay, sir.
Okay. See you next week then. Bye-bye. I think, this long weekend, it's heartening to see that all of you are here for a long weekend. So, good.
Thank you, sir.
Thank you.
Yes, sir.
Okay.
Thank
See you
you,
next
sir.
week.